Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and here we are going to solve another gate question that was asked in the year 2011 for 1 mark. And this question is related to context switching, right? So let's see. So the question goes something like this: let the time taken to switch between user and kernel mode of execution be T1, right? While the time taken to switch between two processes be T2, right? So what are they asking? Which of the following is true? And you have the options like T1 greater than T2, T1 equal to T2, T1 less than T2, or nothing can be said about the relation between T1 and T2. So basically we have two time periods, T1 and T2, as you can see. And T1 is basically the time that it takes to switch from the user mode to kernel mode. That is, it could be vice versa also. It is like switching the privilege level, right? Whereas the second time period, that is T2, it is about the context switching between two processes, right? So let's see what is the solution to this question. So this is the flow diagram of the sequence of events that happen during a context switch. I have talked about this in great detail in the video that I explained how does a context switch happen, right? So if you look at this at a very high level, you can see we have process A. We are executing process A in step one. Then we do some things and do basically switch out the process A and context switch to some different process, that is process B, which is you can see here. So what are all the things that happen here? So first thing is that we transfer the control from the user process to the operating system via a trap. A trap is basically an event which includes which basically transfers the control from the user process to the operating system. And examples of trap events are system calls, exceptions, and interrupts, right? So once the control is with the OS, then the OS handles the trap. Basically, it will save all of the user process registers, right? Then it will determine the cause of the trap, and depending on the cause of the trap, it will invoke the appropriate trap handler, right? Let's say this trap is due to a timer interrupt, and when we have a timer interrupt, in that case, the handler that is invoked will be the scheduler. So the scheduler will pick a process, right? It will run some algorithm, pick a process, and select the next process that has to be allocated the CPU. So in this case, let's say it's process B. Once the selection is done, then the actual context switch happens in step 4. So if you see step 4, this arrow that you see, this includes both. That is, it also includes handling of the timer interrupt. It includes running of the scheduling algorithm, and finally, it also includes the context switching, where actual switching of register happens. Once that is done, the switch is complete, and now we are ready to return to the next process, the one that the scheduler has selected. So when you prepare for return, you restore the registers of process B, and you execute the return from trap instruction, and then you go to execute the user process. So this was the brief recall of the sequence of events that happened. Now coming back to the question. So we have to compare the time that it takes to switch from user mode to kernel mode and the time that it takes to switch between the two processes. So if you see this diagram here, when we are entering the kernel, we are switching from user mode to kernel mode. So this blue arrow signifies that we are executing in user mode. This is user process code, this blue region, and this red region is the kernel region. We are signifying that when these red arrows signify that we are executing kernel code, obviously in kernel mode. So this arrow that you see when we are entering the kernel via a trap, here we make the switch from user mode to kernel mode, and this arrow that you see here, we switch from kernel mode to user mode. And somewhere here, right in step 4, we do the actual context switch. So let's look at both of these events in more detail and see how much time it takes. So if you talk about switching between kernel and user mode, then it is as simple as flipping a bit in the CPU register, in one of the CPU registers, right? So the CPU has a register which has a bit, which is the privilege mode bit, and when you execute the trap instruction, which basically transfers the control to the operating system in case of a system call, exception, or interrupt, this is the trap instruction that is executed, right? As part of the trap instruction in the hardware, this bit flipping is happening, right? So you can see privilege mode switch happens instantly in hardware during a trap, right? So this diagram, if you see, during this switch, all of these happen in the hardware in like atomically as part of the trap instruction. So the trap instruction in the hardware changes the privilege mode. So this is quite a fast this event, that is changing the privilege mode. This action is quite instant. It happens in the hardware with one instruction, that is a trap instruction. So the trap instruction does some other things also, right? That is like jumping to a fixed location, which is the trap handler. But as part of the trap instruction, this flipping of the privilege bit, or you can say raising of the privilege mode, happens instantly, right? The same is true for the return path. In the case of return from trap instruction, the privilege is dropped instantly from the kernel mode to the user mode. So this operation, that is that takes time t1, the operation of switching between kernel mode, is instant. It is done using the trap instruction when we are flipping from user to kernel, and the return from trap instruction when we are flipping from kernel to user. So this operation does not take much time. It is instant. It is done in the hardware, right? Now let's talk about context switch between two processes. What happens when we do a context switch? So basically, essentially, a context switch involves saving the registers of the current process in the context which resides in the process control block, and loading the registers from the context of another process. So I have talked about this in the video where I described context switch. So let me uh, recall what we studied there. So every process is represented by a process control block, right? So the process control block is like a repository which has all the necessary information that is required to represent a process. And generally, these process control blocks come as C style structures, right? So a process control block is a data structure, often a C-style structure, which contains all of the information that is required to represent a process. So this is the process control block from the XB6 operating system. So we have been talking about the XB6 OS throughout this course, and we have seen this process control block in other videos also. So in this process control block, you can see there are several fields, and one of the field is called context, right? What is context? So context is actually a collection of registers, right? One of the registers you can see stack pointer, and then there are several temporary registers also. So context is actually the set of registers, right? And it is part of the process control block. It works like a bookmark for process execution. So I talked about uh, this bookmark analogy in this context switch video. So it's like when you're switching from one process to another, uh, that can be like understood with this analogy, that you can think of reading two books, and when you're switching from one book to another, you put a bookmark to the page where you're last reading, right? So that when you resume reading the first book, you can uh, start from exactly the same point where you had left off. So if you see what the bookmark does in the case of switching, when you're reading multiple books and switching between them, what does a bookmark do? It basically allows us to keep track of what was the last point at which we were reading the book. In the same way, context is like a bookmark. The what the context does is very similar to what a bookmark does. In the case of process execution, we save the state of registers in the context. We take a snapshot of the register state, the contents of the registers, and put it in the context which lives in the process control block. And this serves the same purpose as the bookmark does when we are reading books. Basically, we want to resume the process execution exactly at the same point at which we will leave it, right? At which we will halt it, you can say. So let's take the example. It will help you understand this working of context in a better manner. So let's say we have a CPU. These are the temporary registers, the general purpose registers, which will be used by the processes during the execution. And let's take a hypothetical system which has just two processes, process A and process B. We know that every process is represented by a process control block, right? And so currently you can see process A is executing, and the operating system is pointing to the process control block of process A, which means that it is pointing to the process control block of the current process, right? And there is another ready process, process B. This is the process control block of process B, and this is the context registers which are part of the process control block. So basically here we have taken a snapshot of the registers the last time we halted process B. So the way these things works is that when the process is executing, it is doing the computation using the registers, right? Everything happens in the registers. All of the computation finally happens in the registers. So when a process is executing, right, the state of the registers keep on changing. So the state of registers, the values inside the registers is very important. So if at a certain point you want to halt the execution of a process, you have to take a snapshot of the registers, so that you, when you resume that process, you resume at exactly the same point, right? It is like marking the book number in the using the bookmark, right, while reading a book. That is what is like taking the snapshot of the registers. So we are assuming that at some point in the past, process B had been halted, and this is the snapshot of registers, right? So now let's see what happens when we do a context switch from process A to process B. So let's say the operating system decides that it will deallocate the CPU from process A and it will halt it. So it halts it, and what it does is that it takes a snapshot of the registers at this point and stores all of these registers in the context field of the process control block, right? So if you see, there was no registers here before, but now once we have halted process A, we are taking a snapshot of the registers. Like at this point, whatever was the values, we'll put it in the context structure inside the process control block, right? Recall how the context look like. This is how the context look like, and it lives in the process control block. So that is what we are doing. We are taking a snapshot. Once we have done that, we have halted process A, and then we bring in process B. How do we do that? We load the register values of process B into the CP registers, and that is how we basically restore these registers and start executing process B exactly from the point we had left it at some point in the past, right? So this is how this context switch happens. It is essentially uh, saving the registers for one process and loading the registers for another process, right? It is like when you're reading multiple books and we switch between books, what you do, you put a bookmark in one book, right, and you pick another book and start reading from the point where the bookmark was there in the other book, right? It's very similar to that. Now coming back to this question, this was about the things that happen in a context switch. What are all the things that happen in the context switch? We said saving registers, loading registers. And let me, before I tell you the answer, I also wanted to show you one thing. So here is the code for context switch in XB6 operating system. As you can see, you don't have to understand it fully. It's a low level piece of assembly code. The thing that you have to understand here is that this is assembly code, and we are storing the registers, we are loading the registers. This is the saving of registers for the first process. This is the loading of registers for the second process. So you can see at least there are like uh, in this part there are 12 instructions, I think. So there are multiple instructions that is required to make a context switch happen. At least 20 to 30 loads and stores are there here, right? So this definitely takes more time than switching from kernel to user mode or user to kernel mode, which happens in just one single instruction using a trap instruction, right? So let me go back. What we discussed in case of switching of privilege levels, we said that this is just flipping one bit, right? To switch from kernel to user or user to kernel is just one bit and happens instantly in hardware using one instruction. But context switch, this is a piece of code that will be executed by the software, and you can see multiple instructions are required, and that too these are memory instructions, loads and stores. So this will take time, right? You're loading register values in the memory, and you're also storing and loading. So these are memory operations and many of them, so this will take time. So obviously switching between kernel and user mode is faster and instant as compared to switching between two processes, which requires loading and storing and loading several registers, right? So the answer, as you can see, is T1 would be less than T2. T1 is the time for switching between user and kernel mode. As I said, it is instant and takes just one instruction, the trap instruction or the return from trap instruction, whereas the time to switch between two processes, it will be much more because it involves several memory operations where we save the registers for one process, several of them, and load several registers for another process, right? So T1 is less than T2. Option C is the answer for this question, right? So guys, this was it for this video. Thank you very much for watching. I will see you in the next video. Thank you.